So last time we were talking about logarithmic differentiation a little bit, differentiating like e to the stuff and natural log some stuff. I kind of wanted to continue on in that way just a little bit. Well, then actually a lot, like, and then talk more about a few other things in that same sort of venue. I was also looking at your various homework assignments. Oh yeah, there's a couple things. Yeah, before we do that, there is one thing I should point out. Let's do one more implicit differentiation problem with an extra kind of twist. Oh, let's see. I'm going to make something up. Sure. So I want to find. Up. I had turned it on. What happened? Good question. What did happen? Oh, I see. I pressed the button over here. Thanks. Now, thank you. Appreciate it. Find the equation of the tangent line to, let's say we have, sure, why not, x minus 2y cubed plus 4y squared plus 3xy equal to, let's see here, let me think for a second. 2, 6 equal to 10 at the point 2, 1. And then for a second part, we will also find the equation of the normal line. So, usual deal, right? We're going to find the equation of the line by finding the slope and the point. We already have the point, we just need the slope. So we're going to differentiate both sides. So taking the derivative of both sides with respect to x, we've got some stuff cubed. The derivative is going to be 3 times our stuff squared times the derivative of the inside, which is going to be 1 minus 2y prime. Plus the derivative of 4y squared is going to be 4 times 2y times y prime, or 8y times y prime. And then for 3x times y, I'm going to treat it as the product of 3x and y. So it's going to be the derivative of 3x times y plus 3x times the derivative of y equal to the derivative of 10. Cursor's terrible there. And now, to find the slope of the tangent line, we're just going to plug in the point right now. Right? If you're doing implicit differentiation, you're specifically asked to find the slope at a particular point. Don't do all the algebra without plugging in the point. Plug in the point first. So we're going to plug in 2 for x and 1 for y. Notably, this whole part's going to be 0. We're going to get 3 times 2 minus 2 squared times, it doesn't really matter. That's all going to be 0. Plus 8 times 1 times y prime, plus 3 times 1, plus 3 times 2 times y prime is equal to 0. So let's see, I've got 8y prime plus 6y prime. I've got 14y prime equal to negative 3. So my slope is going to be negative 3 over 14. Whenever it's implicit, if you're just finding the slope of the particular point, don't do all the algebra of finding y prime in terms of x and y. Plug in your point first. It's almost always what's intended. So now, for my tangent line, I've got the point of 2, 1. I've got the slope of negative 3/14. So I'm going to use the point slope form and say y minus 1 equals negative 3/14 times parentheses x minus 2. And sure, we could solve for y if we needed to. I don't really think we need to, but if we wanted to, we could say that y is equal to negative 3/14 times x. Negative 3/14 times negative 2 is positive 6/14. Then we could add on a 1, giving us y equal to negative 3/14 x plus 6 plus 14 is 20/14. Sure, I could reduce that fraction, but if instead you were asked to find the equation of the normal line, all the work is the same. The only difference is, well, what does normal even mean? For lots of things. But in mathematics, normal means perpendicular or orthogonal. So we're just trying to find the equation of the line that's perpendicular to the curve at the same point. So if, for example, our curve looked vaguely like this, and we're finding the tangent line right there at the point 2, 1, then the normal line is just going to look like this. Same point, 2, 1, different slope. In fact, the slope of the perpendicular line, which is the negative reciprocal. So for the normal line, our point is still 2, 1, but our slope now, instead of being negative 3 over 14, is going to be positive 14 over 3. And then same way of writing the equation of the line. We're going to say that y minus 1 is equal to our slope, which is 14 thirds, times x minus 2. We are going to get a different y-intercept because unless the point of tangency or normalness is the y-intercept, these two lines won't have the same y-intercept. Y-intercepts over here are very different. Solving for y, we're going to get y equal to 14 thirds times x minus 28 thirds plus 1, which is going to be y equal to 14 thirds x minus 28 plus 3 is minus 25. So that's how you find an equation of a tangent and the normal line to a curve at a particular point. The normal line is just like an extra little piece where you're like, oh, same idea, different slope. Let's continue on. So last time we had started talking about taking derivatives of things like 4 to the x or e to the x, or well, we kind of already e to the x, but like we got a little more complicated with our exponential derivatives and our logs to different bases. And there's kind of a general idea about how this all works. So let's kind of go back just for a minute and say, what if we had, for example, let's start numbering things, James. What if we want to take the derivative of y equal to 6 to the x? Last time we did it one way, where we said we wrote it as e to the natural log of 6 to the x, then kind of brought the x down. I'm going to show you a different way of doing it this time, just to kind of show you something else that's also valid. So another way of doing the derivative of this is with logarithmic differentiation. So we just take the natural log of both sides and then bring the x down. That's kind of whenever you have a variable in your exponent, a common method of dealing with that is taking the natural log of both sides. So we're going to bring the x down with the natural log of y equal to x times the natural log of 6. And now we're going to differentiate both sides. The derivative of the natural log of some stuff, or the natural log of a function of x, is going to be 1 over the function times the derivative of the function. Just applying the chain rule. Or you could say we're using implicit differentiation. They're kind of the same thing, right? Implicit differentiation, you're really just using the chain rule all the time. You're saying every time, oh yeah, y is a function of x, I have to multiply by its derivative at the end of that process every time. On the other side, we have x times a constant. And the derivative of x times a constant is just the constant. Natural log of 6 is a constant. It's not lovely, but it is just a constant. Just like the derivative of 7x is 7, the derivative of natural log of 6 times x is natural log of 6. And then we solve for y. We get y prime equal to y times natural log of 6, which gives us y prime equal to, I'm going to plug back in the fact that y is equal to 6 to the x. We get 6 to the x times the natural log of 6. Let's go a little more general. Meaning, instead of just having a different base, what if my exponent was a little bit more complicated as well? So what if I had something like y equal to 4 to the x cubed plus cosine of x? What I'm trying to work up to here is not having to do this every time for these problems where your base is a constant. But it's still nice to have seen this. So we're going to do this one kind of the long way as well, and then we'll talk about the shorter way of doing it. So we have the natural, or sorry, using logarithmic differentiation, we have the natural log of y equal to the natural log of 4 to the power of x cubed plus cosine of x. We're going to bring that whole power down. So the natural log of y equal to all of x cubed plus cosine of x multiplied by the constant natural log of 4. Oh, by the way, quick aside here. I noticed that instructor no Seems like he uses log for natural log instead of ln. Something just you need to be aware of. If you're in this class, log means log base c. It does not mean log base 10 apparently. So make sure that you're aware of that. It's not that atypical to use that notation. It's just not how we usually do it in this class, but it certainly is not that weird. Differentiating both sides. Whenever you differentiate the natural log of y, you're always going to get 1 over y times y prime, assuming the y is a function of x. On the right-hand side, same kind of deal as before. We're going to have the derivative of x cubed plus cosine, which is 3x squared minus sine of x times the constant that's just hanging out there. Solving for y prime, we get y prime equal to y times 3x squared minus sine x, all times natural log of 4. Or plugging back in that y prime is equal to this 4 to the x cubed plus cosine, we get y prime equal to 4 to the x cubed plus cosine of x times the derivative of x cubed plus cosine of x times the natural log of our base. And that's the general pattern. If you have, in fact, let's write it down here. So I'll write two things. If your function is some base to the x power, the derivative is that same thing multiplied by the natural log of your base. If your function is a little more complicated, if your exponent is, I meant to write an f there, sorry, this would be an f of x. Sorry, if your f of x is some base to something more complicated than just x, well, just like every other time we've taken a derivative, if your inside stuff is more complicated than just x, we apply the, we end up using the same sort of pattern for the differentiation formula and then throw in a derivative of your stuff at the end of the process. So just like the derivative of b to the x is b to the x times natural log of b, the derivative of b to the stuff is going to be, sorry, apologies, I should be writing a comma there, not an equal sign. The derivative is going to be b to the stuff times the derivative of the stuff, and then the natural log of b. So what I'm trying to say is we don't have to go through this process of logarithmic differentiation for these problems. We can kind of apply a formula and say, okay, great. If my function, for example, was 3 to the 3 to the x cubed again, sure, because I'm unoriginal, plus cotangent of x. To take that derivative, we're just going to throw this formulaic way of doing it at. We're going to say, okay, great. We know the derivative of 3 to the stuff is going to be 3 to the same stuff multiplied by the derivative of that stuff, which is 3x squared minus cosecant squared of x. And then we have to throw in a natural log of 3. That would also work if our base was e. If it was the derivative of e to the x cubed plus cotangent, we would get e to the x cubed plus cotangent times the derivative of x cubed plus cotangent times the natural log of e, which is 1. So this formula works. This is actually the most general way of writing it, is if your function is some base to some g of x, the derivative is the same thing times g prime times natural log of your base. And in a similar way, logarithms with a different base have a very similar structure. So let's go that direction, and then we'll kind of sum it all up. Yeah, and then we'll do that. Sure. Sorry, trying to keep things in order here. So we've seen already that the derivative of the natural log of x is 1 over x. And the derivative of the natural log of something more complicated, like let's be a little more original here, e to the x plus secant of x. Same idea. It's going to be 1 over your stuff multiplied by the derivative of your stuff, which is e to the x plus secant of x times tangent of x. And no, nothing cancels there. It's so sad. Nothing cancels. Stop. It's fine. It's okay to be stuck. If your base is different, there's a couple ways you could go. So if I wanted to find the derivative of log base 2 of x, probably the easiest way to accomplish this is to use the change of base formula. When you have a log with a base you don't like, you can rewrite it as a log with any base. I'm going to write this as the derivative of the natural log of x divided by the natural log of 2. And then to make it a little bit more obvious, we're going to reimagine this as 1 over the natural log of 2 multiplied by the natural log of x. You know what 1 over the natural log of 2 is? A constant. And constant multiples just get to hang out when we differentiate. So we're gonna end up getting 1 over the natural log of 2 times 1 over x, the derivative of natural log of x. And then if things get more complicated, like say we want to find, sure, the derivative of the log base 7 of x to the 6 plus 2x squared. Same idea. We don't really have to rewrite it, but we're going to. We're going to rewrite this as the derivative of the natural log of x to the 6 plus 2x squared divided by the natural log of 7. And again, I'll just state, dividing by the natural log of 7, you're really just multiplying by a constant. I do think it's worthwhile to at least be able to think of it as, oh yeah, it's that constant, 1 over natural log of 7, multiplied by my function, natural log of x to the 6 plus 2x squared. And now when we differentiate, our constant multiple gets to hang out. And then the derivative of the natural log of some stuff is going to be 1 over the stuff. And then we multiply by everybody. Multiply by. Thank you so much, everybody. The derivative of the stuff. You should be dreaming those words. The derivative of the stuff. You should be, oh yeah, the derivative of the stuff. I'm multiplying by the derivative of the stuff because of the chain rule. So just like with exponential functions, when your logarithmic functions have a different base, the natural log of that base shows up. It's just for exponential functions, we multiply by the natural log of the base. For logarithmic functions, we end up dividing by the natural log of the base. So the general kind of rule here is the derivative of log base b of x is just 1 over x times the natural log of that base. And then if your stuff is more complicated, the derivative of log base b of some more complicated stuff is going to be 1 over your stuff. I don't know what that's about. 1 over your stuff. The natural log of b also shows up down there, and then we multiply by the derivative stuff. So that's how I kind of think of the different bases acting. The functions still act like they normally when we differentiate them. We're just getting either a multiple of the natural log of our base, or we are getting a multiple, and we're either multiplying by it or dividing by it if it's exponential or logarithmic. So you all should try the next two questions on your own. Try both of these. Find the derivative of 2 to the x to the 4th plus sine of x. And then the second one that I'll write, but I won't say. Sure, of course. I will also remind everybody that I do post the notes on Canvas. Not that you're not welcome to take pictures, just they are available later on as well. Couple. Let's take a look and see what we've got. So again, while we certainly could use logarithmic differentiation for this first one and take the natural, like, write it as y equals and take natural log both sides, we really don't need to do that if our base is a constant, like 2 or like 5. So here, we're just going to say the derivative of 2 to the stuff is 2 to the stuff times the derivative of our stuff times natural log of 2. Does not matter which, because it doesn't matter what order you say the words in. Doesn't matter which order you write the things in if it's multiplication, right? I could have done 2 to the stuff times natural log of 2, then times the derivative of the stuff. If that makes more sense to you. Similar-ish deal here. I've got log of some stuff. I know the derivative is 1 over the stuff times the derivative of the stuff. I will be honest, the way I usually write this is actually kind of not nice. I almost always write this as 1 over my stuff times the derivative of the stuff, which is 8x to the 7th. The derivative of cosecant is negative cosecant cotangent, so it's going to be positive cosecant of x, cotangent of x. And then I put my 1 over the natural log of 5 at the end. I know that looks maybe like the dumbest thing ever, but that's just the way I say it in my head, so that's the way I like to write it down. But most people will probably write it as like these two parts together, and even putting this in the numerator if you wanted to. I don't really care how it looks. I just care that it's right. Sure. Okay. Now, all that said, there are some functions that absolutely require logarithmic differentiation. Specifically, something like the following. I start, my numbering is always just ridiculous. Something like x to the x. That function, we cannot use any of these rules we've talked about because we don't have a constant in either the base or the exponent. It's definitely, we can't use like the power rule here, and we can't say the derivative of x to the x is x to the x times the derivative of x times the natural log of x. It just doesn't work. We have to use logarithmic differentiation here. And so I'll point out, if someone writes it this way, especially, it's kind of extra cruel because they're hiding the fact that you need to write it first as y equals something. So the first step here, if you're trying to actually do this, is to write it as y equal to x to the x. And then take the natural log of both sides. And then the whole reason for taking the natural log of both sides is to help us get that thing that's in the exponent out of the exponent. That's why we do this. So then we're going to say that the natural log of y is equal to x times the natural log of x. Then we're going to differentiate both sides. And unlike the previous times we've done this, on the right-hand side, we're going to have to use the product rule because we have a function of x multiplied by another function of x. So differentiating both sides, we're going to have 1 over y times y prime. Product rule on the other side, we're going to get a 1 times natural log of x plus an x times the derivative of natural log of x is 1 over x. I think you can do this last 2 steps in 1 step, but I'm going to do 2 steps. So I would say you can probably skip writing the y prime is equal to y times the natural log of x plus 1. And instead jump straight to saying, but I know that y is equal to x to the x. So y prime is equal to x to the x times parentheses the natural log of x plus 1. Technically, there is a formula you can memorize for this process of taking the derivative of f of x to the g of x power. It is not something you should memorize. I have never taken the time to memorize. I've looked at it like, yeah, you could memorize it. You should know this process. This is what your teachers actually want you to know, is how to do this process. So with that in mind, let's do one more example. I can probably fit it in over here. Sure. So let's say we have something a little bit more interesting, like, where'd you go? I'm sorry, I had looking at something. Ah, that's fine. Yeah, sure. The derivative of x to the sine of x. So I want you all, so first step, I want you all to write it as y equal to x to the sine of x. And then your next 2 steps should be taking a natural log and bringing down the power. Do it. After we've gotten that the natural log of y is equal to sine of x times the natural log of x, now is the time to differentiate both sides. Whenever you do this process for something with x to a power or something with x, you're always going to end up using the product rule here. There might be other stuff as well, but for sure the product rule is going to come into play. So you're going to get 1 over y times y prime equal to the derivative sign, which is cosine of x times the natural log of x left alone, plus sine of x left alone times the derivative natural log of x, which is 1 over x. Simplifying a bit, again, I think you can make this one step, but I'm going to make it 2. Y prime is going to be y times cosine of x times natural log of x plus, instead of writing sine of x times 1 over x, let's write it as sine of x divided by x. And then finally, we should fill in what y is equal to, right? Unlike implicit differentiation, where like your derivative is in terms of x's and y's, if you're starting off with y as a function of x, our derivative should end as y as a function of just x. So we should replace y with the fact that it's equal to x to the sine of x and say our derivative is equal to x to the sine of x times cosine of x times natural log of x plus sine of x divided by x. That's our final lovely answer. It is our final answer. There is no further simplification I can do here. If you're asking yourself, why am I not replacing sine of x over x with 1? Because I'm not taking a limit, right? Sine x over x is only equal to 1 when you take the limit as x approaches 0. So this is as simple as it gets. We cannot simplify this any further. All right. Yeah, sometimes. Sure, I guess we have to talk about that. I will also point out, looking at the homework for Chan, he assigned you guys a lot of problems where you use logarithmic differentiation in the way we talked about last time, where you have like some sort of quotient or product of a bunch of things, and you use a logarithm to break that up into many pieces and then differentiate it and then multiply by y afterwards. So similar process, but slightly different application, which we definitely did talk about last class. So moving along, yeah, we might come back to that, but we should talk about inverse derivatives. Inverse derivatives are kind of weird, I think, or maybe it was just hard for me when I learned it, so I feel like it's kind of weird. It's probably not that weird, but I feel like this example actually makes it a little bit more clear about what's going on. So we're going to start off by graphing two functions. We're going to graph f of x equal to x cubed plus 1, and we're also going to graph the inverse function. We're not actually going to find the inverse yet, although it's not that hard to find. We're just going to graph it by graphing it, which I know sounds silly the way I said it. It sounds like a tautology, but what we're going to do. I'm going to plot a few points here. I'm going to plot, let's see, for this function here, I'm going to plot x equal to -1 and y equal to 0. And x equal to 0 and y equal to 1, and x equal to 1 and y equal to 8. Sure. Or 1 and 2. What am I? 1 and 8. And then 2 and 9. Sure. It looks vaguely like this. The point I'm really focused on here is the point 2, 9. And yeah, we've got some other points. 1, 2, 0, -1, 0. And what I actually want to point out here is that if you were just given this graph and asked to graph the inverse, the way you could start graphing the inverse is by literally taking every coordinate pair you have and interchanging x and y. Because how do you find the inverse function? By interchanging x and y. So if I plot all the points where x and y are interchanged, like the point 0, -1, and 1, 0, and 2, 1, and 9, comma 2, I've got a decent idea of what the inverse looks like. Sure, 9, comma 2. Yeah, that's not my best, maybe. So here's what my inverse function looks like. Yes, we could also find it. If you start with this here, and you have y equal to x cubed plus 1, you can switch x and y, and then solve for y. And that certainly does look like the cube root function has been shifted 1 to the right. So yeah, that's our inverse function. So there's a lot of symmetry going on here. In fact, one way to think about inverse functions is that they're literally reflections of each other across the line y equals x. If you, and again, you know, my graphing skills notwithstanding, those look like they are reflections of each other across the line y equals x, give or take. The question I want to answer is, how does the slope of f of x at x equal to 2 compare to the slope of f inverse at x equal to 9? Well, let's take a look. First one's not too hard. F prime of x is equal to 3x squared. So if I plug in 2, f prime of 2 is equal to 3 times 2 squared, which is 12. Pretty steep, which looks reasonable, right? That slope there certainly seems like it's pretty steep. Let's look at the inverse. By actually just, yeah, looking at our inverse function. So if I take the derivative of f inverse, which is always a pain to write, and that looks spelled, wow, I did it. Let me write, speaking of a pain to write, let's try writing that again. The derivative of f inverse of x is going to be the derivative of the cube root of x minus 1, which is x minus 1 to the 1/3 power, which is going to be 1/3 times x minus 1 to the negative 2/3 times 1, technically, right, because of this rule. And then we plug in 9, I'm going to get the following. The derivative of f inverse of x evaluated at x equal to 9, that's going to be 1/3 times 9 minus 1 to the negative 2/3. 8 to the negative 2/3 is, let's see, 8 to the 1/3 is 2. 2 squared is 4. 2 to the negative second is 1/4. So we're going to get 1/3 times 1/4, which is 1/12. And it is not a coincidence that these slopes are reciprocals of each other. It is very much based on the fact that these have symmetry across the line y equals x. So if here the slope is over 1 and up 12, here the slope is over 12 and up 1. That's kind of it, really. But it tells us that we can find the derivative of the inverse by taking the reciprocal of the derivative of the original function evaluated at the matching point on the original function, which is kind of always the part that throws me off, is you have to like kind of think about what the point is. So how do we use this? In a number of ways. Let's actually write down the result. So there's a theorem, kind of annoying. It's sure. So how to find the slope of an inverse function. The way I would like to write it is, we're trying to find the derivative of the inverse function at some b. It's going to equal 1 divided by the derivative of the original function at not the same x coordinate though, right? Instead of finding the, right, I'm not finding, so like if I'm trying to find the derivative of this at 9, I'm finding the derivative of the 1 over the derivative of the original at x equal to 2, which is the inverse of 9. So it's 1 over f prime of f inverse of b. Or written as some textbooks write it, the derivative of f inverse with respect to x at x equal to b is equal to 1 over the derivative of f with respect to x at x equal to f inverse. Again, kind of annoying notation, but that's what we've got. Again, the idea is really kind of laid out in the picture from before, right? Just these two curves that are inverses to each other have slopes that are reciprocals of each other, but the same sign still. So what kind of questions can we ask about this? Well, kind of annoying ones, but here's one example. We want to find the slope of the tangent to the inverse of f of x equal to x to the fifth plus x cubed plus x plus e to the x minus 1 at the point. Oh, did I blow that there? Sorry, it's apologies. Did not mean to write that last part. Yeah, that's annoying. Sorry, apologies. Didn't mean to get the last part in there. At 3, 1. So normally, if someone asks you a question like this, you'd be like, well, I'm just going to find the inverse function, take its derivative, and plug in the point. Can't do that here. I don't know how to find the inverse of that. It's probably impossible. So here's what we're going to do. We're going to say, well, I know that the derivative of the inverse at whatever point I'm looking for. What point am I looking for? Is it 1 or is it 3? Let's see here. F of 1 is equal to 3. Just looking at the original function, right? If I plug in 1, I get 3 out. Meaning f inverse of 3 is equal to 1. So I'm trying to find the derivative at 3. I'm really going to find the 1 over the derivative at f inverse of 3. So it's going to be the derivative of f inverse at 3 is going to equal that. I will fully admit that I often get this wrong in my head. Is going to be 1 over f prime of f inverse of 3. Which is going to be 1 over the derivative of f, which is going to be 5x to the 4th plus 3x squared plus 1, evaluated at f inverse of 3, which is going to be x equal to 1. That's going to be 1 over 5 plus 3 plus 1, which is 1 over 9. Kind of weird. Really kind of weird, actually. It feels very like you're almost doing things backwards.
Why did we use 1 if it was f prime of f inverse of 3?
Because f inverse of 3 is equal to 1. And the way we know that is because we know that f of 1 is equal to 3. But also they gave us the point here, right? They told us that for the f inverse function, and I didn't like explicitly make that super clear when I wrote it down, but right, they're telling us to find the slope of the tangent line to the inverse of f at this point that's on f inverse. So they're telling us, oh, f inverse of 3 is equal to 1, but we can also see that by looking at this function here. If I plug in 1 here, what do I get out? Right. And there's this relationship between function and inverses where you switch the input and the output. We know that if f of 1 is equal to 3, which it clearly is, that f inverse of 3 has to equal 1, which they've also told us here.
So you plug in 3 there, you should put also 1 in.
So I'm plugging in 3 to f inverse, but I don't have the inverse function. So right, it's kind of a trick, is how it feels to me, to be perfectly honest. Let's look at another example and we'll see if we can kind of make it a little bit, maybe not make more sense, but kind of just grasp more how we do this process. And there is a good reason for doing this. It's not just for the sake of this theorem. This theorem to me feels kind of like, okay, fine. But we'll talk about it and then we'll do with the real thing. So let's say we have this example. We want to find for f of x equal to e to the negative x squared plus x we want to find the derivative of the inverse function evaluated at x equal to 1. Okay, so here's the question you have to ask yourself. Is 1 the thing that's easy to plug in here or to the inverse? Which we don't have, by the way. We don't have the inverse. Well, it's kind of weird. If I plug in 1 here, do I get something nice out? I would highly say no. E to the -1 plus 1. I mean, it's not like terrible, but it's not an integer. I'm thinking integers. I'm thinking of nice numbers. So I might try to think about what could I plug into this to get out 1? Well, there's kind of an obvious choice. Maybe not obvious, but usually you guess something where you think it's going to turn out to be nice. What's the only thing you can raise e to a power of and still get an integer most of the time? 0. If I plug in 0, what do I get? I get e to the 0 plus 0, which is 1. Which tells me if f of 0 is equal to 1, then if I interchange them, f inverse of 1 is equal to 0. So here's what's going to happen. I know for this derivative of the inverse, it has to be 1 over the derivative of the original. So it's going to be 1 over f prime. But the thing is, I don't want to plug in 1 to my function here, or its derivative. I want to plug in the inverse. So it's f prime of f inverse of 1. That's what the theorem says to do. Not that that's a good reason for doing something, but like that's what the theorem says. It's 1 over f prime of f inverse. Let me show you graphically again. Right? So if our function looked like, I'm just going to make it look kind of interesting. Right? If our function looked like that, if this is our original function, and here's our inverse, which probably doesn't look exactly like that, right? But if we're trying to find the slope here at the point 1, 0, we're going to find the reciprocal of the slope here at 0, 1. So we're going to find f prime of x, which is the derivative of this, which is going to be e to the negative x squared times negative 2x plus 1. And we're going to plug in 0 to that. So f prime of 0 is going to be 0 plus 1, which is 1. So the slope there is 1. And then to find the slope here, it's going to be 1 over the slope there, which is also going to be 1, which is kind of boring. It's kind of not my favorite example. So we're going to get 1 over f prime e to the negative x squared times negative 2x plus 1 evaluated at f inverse of 1, which is 0. It should be the number that's nice to plug in. So we're going to get 1 over e to the 0 times 0 plus 1, which is just 1 over 1, which is 1. Yes, it's kind of annoying that both slopes are 1, but the reciprocal of 1 is 1. So that's what you get.
So are the tangent lines of inverse functions always parallel to each other?
No, this is a unique example. In the previous example, they were definitely not parallel, right? So this one here was 1/9, and the other one was going to be positive 9. So if I graphed, okay, so let's take a look here real quick. I should have done start. That's not Desmos. So if we look at the original function, which was y equal to x to the 5th plus x cubed plus x, and we look at the point 1, 3. So that point right there, the slope of the tangent line is positive 9. Check it out. You can zoom in there. Yeah, that tangent point there, that tangent line clearly has a slope of 9. If I graph the inverse function, which I wouldn't be able to find the inverse function on my own, but it's super easy in Desmos, switch x and y. So here's the bonkers looking, maybe it's not that bonkers, I don't know. Here's the inverse function. That's actually really cool, I think. Oh, maybe I'd like to. So there's my inverse function. Let's go back to there's my inverse in purple. And if I find the slope of the inverse at x equal to 3, so if I plug in the point 3, 1, there's the point, there's the place I'm trying to find the slope of the tangent line at. And it's going to be equal to 1 over the slope of this tangent line. It's going to be 1/9. And you can see that if I write the equation, y minus 1 equal to 1/9 times x minus 3. Oh yeah, that line has a tangent line that has a slope of 1/9 in correspondence to the tangent line with a slope of 9 for the original function. So back to the work we did, right? When we were asked to find the slope of the tangent to the inverse at the point 3, 1, what we really did is we found the slope of the original function at 1, 3, specifically at x equal to 1, which is f inverse of 3, and then did the reciprocal of that to find the slope of the thing we wanted. That's what's going on. Hopefully that makes a bit of sense. It's kind of wonky, but it does work. And for Chan, there are a couple questions about that. I think problem 4 specifically on your homework assignment. Now, the reason we really like to talk about this is because it helps us find a few more derivatives of new functions, specifically the inverse trigonometric, which we'll cover if you haven't already. We should definitely talk about. So we want to find. Let's see. Before I get too ahead of myself, let me make sure I'm really not get too crazy about finding derivatives right away. Let me see. Let me see one more thing here. Yeah, we should talk about that for a moment. Okay, so let's talk about graphing the inverse trig functions. In my opinion, there's really only 3 you need to know about, although we can talk about all 6 of them if we want to. Let's start with sine. So first we're going to start by graphing y equal to sine of x, which has the usual shape. I'm going to graph 2 periods of it from negative 2 pi to positive 2 pi. It's going to look, it'll be too perfect here. Wow. It don't have to be too perfect, but it'd be good to be kind of good at it. Okay, there's my not great graph of sine. And what I'll point out here is that when you graph this, if you invert the relationship between x and y, you don't get a function. This original function is clearly not passing the horizontal line test. It is not 1-to-1, meaning the inverse relationship is not a function. It doesn't pass the vertical line test. If you just graph x equal to sine of y, you essentially get the sine function, but on the y-axis instead of on the x-axis. Taking a look at this, kind of problematic. We have a domain that goes from negative 1 to 1, and our range is kind of everything, and it looks like kind of like this. So make sure I can graph this right here. Wow, okay. So there's our inverse relationship. I'm not saying the word function because it's not an inverse function. So what do we do to make it a function? We restrict the domain of the original thing. So the way you turn this inverse relationship into an inverse function is you say, well, I'm going to take my original function, but I'm only going to go from negative pi over 2 to pi over 2, where that section of the function is 1-to-1 and passing the horizontal line test. If I just invert that, I get this section from here to here, which is also going to be a function. The inverse sine function is, in my opinion, a little bit disappointing. There's not a lot of it. So here's the graph of f inverse. Nah, I don't really want to call it f inverse of x. Sorry. Here's my graph of f of x equal to the inverse sine function. It looks like this. It's got a domain from -1 to 1. It's got a range from -pi/2 to pi/2. And it looks like this. Kind of unexciting. A few things about the inverse sine function. The reason I really wanted to talk about this before I got straight into the derivatives is because I want to make sure we all know the value of the inverse sine function, or also known as the arc sine of x function. I would say most people probably prefer this name versus that name. This name makes it more obvious that it's not 1 over sine. It's definitely not 1 over sine. It's not the cosecant function. It's a very different function. Couple things about arc sine, specifically evaluating it. If I wanted to find, say, the arc sine of the square root of 2 over 2, what I'm asking for is what angle gives me a sine value of root 2 over 2? Well, the angle is pi over 4, specifically in radians. And that's true because sine of pi over 4 is equal to root 2 over 2. Right? For an inverse function, doesn't matter if it's trig specifically, the inverse functions interchange the role of the input and the output. So if sine of pi over 4 is equal to root 2 over 2, which it is, then the inverse function has to interchange the output with the input. The arc sine of root 2 over 2 has to equal pi over 4. In a similar way, the arc sine of positive 1/2 has to equal pi over, good question, pi over what? 6. Because sine of pi over 6 is equal to 1/2. And one more, the arc sine of -1/2 is equal to -pi over 6. For the same sort of reason. Take sine of -pi over 6, which is in quadrant 4, you get -1/2. Now, you might ask something like, well, James, why isn't the arc sine of root 2 over 2 equal to 3 pi over 4? That's an angle where sine of 3 pi over 4 is equal to root 2 over 2. And I think that's true, but we have kind of decided as a mathematical community that this is the domain we're going to pick. We've decided that the range of the arc sine function goes from -pi over 2 in quadrant 4 to positive pi over 2 in quadrant 1. And that's it. We're all going to agree. The reason I kind of make a case about this is because that statement is not true when it comes to the arc secant and the arc cosecant functions. Those two functions, there is not agreement about what domain should be picked, and so we kind of ignore them. But we'll talk about them a little bit. But yeah, their graphs are weird because they're like, this is the graph. They're like, this is the graph, and we're right for different reasons. One of the graphs looks nicer. One of the graphs has a better derivative. So talk about that in a minute. Let's talk about the other two trig functions we're going to graph their inverses of right now, though, specifically the arc cosine and the arc tangent. So we'll do the same sort of thing for cosine. For y equal to cosine of x, I'm going to pick part of the domain that's 1 to 1. Still, I should graph it first, maybe. Still go from -2 pi to 2 pi. Cosine goes like this. Wow, those are not the same length, but oh well. And here's where there's a bummer. You don't get to pick the same domain we picked for sine. It's not going to be -pi over 2 to pi over 2, because that part of the function isn't 1 to 1. It fails the horizontal line test. So instead, we're going to pick the domain from 0 to pi. That's the part of cosine that you pick that gets the entire range from -1 to 1 with a domain where you don't have the domain, the range overlapping back on itself. Is it blurry? It is blurry. Sorry about that. There we go, much better. Better, yeah. So we're gonna pick the domain from 0 to pi and then invert that. So our inverse function, f inverse of x equal to the inverse cosine of x, or if you prefer, and we do prefer, f inverse of x equal to the arc cosine of x. Looks like we're going to take this piece here, which has a point of 0, 1 and a point of pi negative 1, and interchange all our xy coordinates. So instead of 0, 1, I'm going to get 1, 0. Instead of pi negative 1, I'm going to get negative 1 pi. And I get 0 pi over 2. It's going to look like this. There's our inverse cosine graph. All of it. That is all of the graph. That's as much as you can ever get. In a similar way with arc sine, you can also find arc cosine of lots of values. Like, for example, the arc cosine of 1/2 is equal to pi over 3. Because cosine of pi over 3 is equal to 1/2. And the arc cosine of negative 1/2 is equal to, prepare for disappointment, 2 pi over 3. Not negative pi over 3. Because cosine of negative pi over 3 would equal positive 1/2. But that's in quadrant 4. So for arc cosine of negative numbers, you have to end up with angles that are in quadrant 2, where cosine happens to be negative. One more, arc cosine of negative root 2 over 2 would be 3 pi over 4. Because cosine of 3 pi over 4 is equal to negative root 2 over 2. So it's a little bit annoying, but it is true that the range of the arc cosine function is 0 to pi, whereas the range of the arc sine function is negative pi over 2 to pi over 2. And again, that's what we've all just decided on. And these decisions, I think, make sense for both arc sine and arc cosine because you're picking quadrant 1, which is kind of like everyone's favorite quadrant, and then the quadrant adjacent to it that meets your needs still, whether it's quadrant 2 or quadrant 4. There's something else I want to say here. No, I don't think so. Not really. Last one that we're going to graph, and then we'll talk about finding some derivatives. Yeah, I think so. Let me just make sure I'm not forgetting anything else interesting here. No, we're good. Yeah. So, arctangent. So for graphing tangent of x, tangent of x has vertical asymptotes at negative pi over 2 and pi over 2. It actually has a lot more than that. Vertical asymptotes at every odd multiple of pi over 2. So pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. It goes on and on. And then it just repeats itself. Just like any trigonometric function, right? They're all periodic. They all do the same thing after however long their period is. 2 pi for sine, cosine, secant, and cosecant. 1 pi for tangent and cotangent. And so on. I don't want to graph it, but I would encourage all of you, if you have a chance, to graph tangent of y equal to x at some point. If you graph the inverse relationship, it's just all these like horizontal tangent things. It just like it just looks neat. If you graph both of them, it looks really neat. There's like a cool kind of grid pattern. You should definitely be playing with Desmos if you're at all interested in math at all. Like if you like math even a little bit, go play with Desmos. It's kind of fun. You can make some really interesting looking graphs and just see some neat things. You don't like math? Well, I'm sorry. You're missing out. But you're here anyway, so good. To graph the inverse, just like every other time, I'm going to take one domain that is 1 to 1. Now, there's lots of choices we could make, but the best choice, the choice everyone did, is to go from negative pi over 2 to pi over 2. That is the standard choice. We don't want to split up our graph in the middle in some strange way. So we're going to just limit ourselves to this, and then we're going to invert it. So when you invert things, you interchange x and y. All y things become x things, all x things become y things. This vertical asymptote at pi over 2 and negative pi over 2 becomes a horizontal asymptote at positive pi over 2 and negative pi over 2. And before, as x got close to pi over 2, y got really, really big, I'm going to switch the letters. Now as y gets close to pi over 2, x gets really, really big. Or as x gets really, really big, y gets really close to positive pi over 2. Okay. So instead of having the point pi over 4 comma 1, we have the point 1 comma pi over 4. Because the inverse tangent of 1 is equal to pi over 4. And the arctangent of root 3 is equal to pi over 3. Something that does come up, not all that much this quarter, but definitely comes up next quarter, is someone asking you what the limit as x goes to infinity of the arctangent of x is. And really it's based on you being aware of this graph and be like, oh yeah, if x is really, really big, what's my graph hitting closer and closer to? Pi over 2. That definitely will come up next quarter for sure. When you're talking about improper intervals. Maybe other places, definitely there. All right, cool. We talked about the things. Let's go ahead and yeah, let's do that one. That's the fun. Yeah, all right. Sorry, I'm all over the place. There we are. I see my notes. Apparently I can't touch this cord. Okay, sorry about that. So all that to say we can now find the derivative of some of these inverse trig functions. Now, you could do it in what I would think is kind of a wonky way, where you use that formula we just talked about before, the 1 over the derivative of the inverse function, which is essentially what we're going to do just in a more logical way. So let's say we want to find the derivative of, yeah, let's be smart about this, y equal to the arc tangent of x. So typically, yeah, cool. Yes, that's what I want to do. So here's what I would do. Whenever you're just like when we found the derivative of the natural log of x, we rewrote it as like, I'll remind you even, we were doing the derivative of the natural log of x, we said y equals natural log of x. We rewrote it as e to the y equal to e to the natural log of x, which is just x, and we differentiated both sides implicitly. Basically taking your inverse function and rewriting it so your original function is showing back up. The thing we already know how to differentiate. So I'm going to do is I'm going to take my y equals arctangent of y. Sorry, my y equals arctangent of x, sorry. And rewrite it as tangent of y equal to x. Something I didn't say, but I should have said a moment ago, is when I read arctangent of x, or something like the arc sine of negative root 3 over 2. The words I'm saying in my head aren't arc sine of negative root 3 over 2. The words I'm actually saying are the angle whose sine is equal to negative root 3 over 2. So when I see this, I'm like, oh, I want to find an angle. The angle that if I took sine of that angle, I would get negative root 3 over 2. Oh, I know what that angle is. It's negative pi over 3. But the point is that if you're taking arc tangent of x and saying it's equal to y, you're saying, oh, I'm looking for the angle, calling it y. And if I took tangent of that angle, I would get x. That's exactly what's happening here. Just interchanging the x and the y. But now, this equation, I didn't even touch anything that time. What's going on over here? Okay, just hold it together for another 12 minutes. Now, the thing about this equation is I know how to differentiate both of those functions. What's the derivative of tangent of some stuff? Secant squared of the stuff times the derivative of the stuff. What's the derivative of x? 1. And now we can solve for y prime. So we're going to get y prime equal to 1 over secant squared of y. Normally, I would write this as cosine squared, but it's actually not in our interest to do that. So we're back having the same sort of problem we had before, where we started off with y as a function of x, and our derivative is in terms of y. It should really be in terms of x. So we have to change that secant squared of y into something with x. There's two different ways of doing this. I prefer what we typically call the triangle method, meaning take your tangent of y equal to x and say it's tangent of y equal to x over 1. Draw yourself a nice little triangle, a right triangle, where the angle is y, and tangent is opposite over adjacent. So tangent of y should equal the opposite divided by the adjacent. Find the third side, Pythagorean theorem. It's going to be, let's see, 1 squared plus x squared equals my hypotenuse squared. So my hypotenuse squared is equal to 1 squared plus x squared. So my hypotenuse is equal to the square root of 1 plus x squared. And then cosine would be 1 over the square root of 1 plus x squared. So secant is the square root of 1 plus x squared over 1, or just the square root of 1 plus x squared. So our y prime here is going to equal 1 over the square root of 1 plus x squared, which is 1 over 1 plus x squared. And that is the derivative of the arctangent function. So it is very true that the derivative of the arctangent of x is equal to 1 over 1 plus x squared. Now, a couple notes here. Technically, I kind of glossed over a point or two here, specifically about the domain and range. So technically, when I found this hypotenuse length, I could have had a plus or minus. Because, right, if I kind of ignore the triangle, like the fact that there's a length, this could be plus or minus the square root of 1 plus x squared. However, since my inverse tangent function gives me angles between negative pi over 2 and pi over 2, which are in quadrants 4 and 1, secant of an angle in quadrant 4 or quadrant 1 is always going to be positive anyway. So I didn't actually need to worry about it being plus or minus because the secant part takes care of it. Also, the whole thing getting squared also takes care of it. But the other two, what I'll say is that for the other derivatives we find in the same way, the same sort of thing happens where there's kind of this issue about what quadrant we're in, but then the trig function we're using makes it work out so that you don't have to think about it anymore. So let's do at least, yeah, we'll do both sine and cosine. They're worthwhile because they actually show something kind of cool. So I'll point out before we do anything else, we just learned a new derivative. The derivative of arctangent of x equals 1 over 1 plus x squared. You already know that means we also know a chain rule version of it, right? If the derivative of the arctangent of x is equal to 1 over 1 plus x squared, then you also know that the derivative of the arctangent of some stuff, I'm just going to use u for the moment, is equal to 1 over 1 plus your stuff squared times the derivative of your stuff. General idea. Whenever you learn a new derivative rule, you should automatically think about the chain rule version of it. Oh yeah, just putting in a different thing for x, multiplying by the derivative of that thing at the end of the day. All right, let's look at sine of x. So for y equal to the arc, sorry, I said sine, I meant to say arc sine of x or the inverse sine of x. The process is the same. We're going to rewrite it as sine of y equal to x. And differentiate both sides. The derivative of sine of some stuff is going to be cosine of our stuff times the derivative of our stuff, and it's going to equal the derivative of x, which is 1. Also, let me write something. So I'll point out here that for y equal to inverse sine of x, note that y is between negative pi over 2 and pi over 2. Just so I can say the things with more confidence at the moment. Solving for y prime here, y prime is equal to 1 over cosine of y. My preference is the triangle method, but just to show you a different way of doing this, you could also just use a trig identity. So I'm going to use I should say specifically, the Pythagorean trig identity. So for sine and cosine, that's that cosine squared of y plus sine squared of y is equal to 1. if I solve for cosine squared of y is equal to 1 minus sine squared of y. And here's where the plus or minus plays a more prominent role. Cosine of y could be plus or minus the square root of 1 minus sine squared of y. But, just like before, we know that the angle y is between negative pi over 2 and pi over 2, which means it's in quadrants 1 and 4, or I should say 1 or 4. And cosine of an angle that's in quadrant 1 or in quadrant 4 always ends up being positive. It has to be positive. You have no choice. Great. What we want. So that means we get y prime equal to 1 over the square root of 1 minus sine squared of y, but sine of y is equal to x. So this is really equal to 1 over the square root of 1 minus x squared. That's your derivative of the inverse sine or the arc sine. Not my preferred way of doing it. I would have much rather drawn a triangle and said, oh, sine of y is equal to x over 1, which is the opposite over hypotenuse. Draw my triangle. My angle is y, my opposite side is x, my hypotenuse side is 1. My missing side using the Pythagorean theorem. Oh, the Pythagorean theorem and the Pythagorean identity over here. There's a reason those are both coming up. That's going to be the square root of 1 minus x squared. And then cosine of y is adjacent over hypotenuse, which is the square root of 1 minus x squared over 1. That's why you get that thing. I like the triangle method better. Also, this triangle idea is going to show up again in 21B when you learn about trig substitution. So I definitely think it's in your interest to think about it this way versus thinking about that. I mean, they're kind of the same, but it's good to see both. Fun fact. It is a fun fact. It's actually a nice fact. It's a good fact. We like this next fact. The inverse cosine derivative has almost the same outcome. Let me show you. Let's say we want to find the derivative of the inverse cosine of x. Well, first I'm going to do the same usual thing. I'm going to start with y equal to the inverse cosine of x. I'm going to rewrite it as cosine of y equal to x. I'm going to differentiate both sides. I'm going to get 1. Sorry, I'm thinking logarithms here. I'm not going to get 1. I'm going to get negative sine of y times the derivative of y equal to 1. Solving for y prime is going to equal 1 divided by negative sine of y. And then using my triangle trick, not my triangle trick. It is important when you do this that whatever your trig function is equal to, you write it as a fraction. So cosine y equals x means cosine of my angle y is equal to x divided by 1. That means my adjacent side is x, my hypotenuse is 1. The missing side is, let's see, x squared plus question mark squared equals 1 squared. So question mark squared equals 1 minus x squared. So my question mark is the square root of 1 minus x squared. So sine of y is opposite over hypotenuse, which is the square root of 1 minus x squared over 1. So then my y prime ends up being negative 1 over the square root of 1 minus x squared. Virtually the same. I'm sorry, you can't quite see that. As the previous one, right? The derivative of arc sine of x was positive 1 over the square root of 1 minus x squared. The derivative of arc cosine of x is negative 1 over the square root of 1 minus x squared. That is not a coincidence. The same thing holds for the derivative of arc cotangent. You should all be able to look back to say, okay, the derivative of arc tangent is 1 over 1 plus x squared. The derivative of arc cotangent is negative 1 over 1 plus x squared. And the same is also true for the derivative of arc secant and the derivative of arc cosecant. Let me see something here real quick. Yeah. So I don't want to get too into the details since we are almost out of time, but I do want to show you what the derivative of arc secant is because it's kind of annoying. So let's say we had y equal to the arc secant of x. I need to first take secant of both sides, getting a little ahead of myself here. So secant of y is equal to the x. And now we're going to differentiate both sides. Secant's a little weird. The derivative secant of some stuff is secant of your stuff times tangent of your stuff times the derivative of your stuff. It's still equal to 1. It's always 1 when we do these problems. Solving for y prime. Y prime is going to equal 1 divided by secant of y times tangent of y. And then, drawing our little triangle, here's my angle y. Secant of y is equal to x over 1. Secant is, well, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. The missing side is going to be the square root of x squared minus 1. And then we're going to, so now here's the part where something weird is going to happen. Y prime is going to be 1 over secant of y is equal to x. Tangent of y is equal to the square root of x squared minus 1. And in my opinion, this is not correct. Here's what's missing. So, sorry, I know. So I know it's like 2:30. Let me just show you real quick here. There are two different graphs for the arcsine, or sorry, for the arcsecant. I know I didn't talk about the secant graph, but let me just show what it looks like. The arcsecant graph that I prefer looks like this. Arcsecant of, wow, brain. Arcsecant of 1 is 0. Arcsecant, yeah, it looks like, wow, do I remember what it looks like? I'm like, yes, okay, it looks like this, sorry. Like that, and then it looks like this. You have a horizontal asymptote at pi over 2. It's like that. So sorry for my very quick graph here. This point's 1 comma 0. This point's negative 1 comma pi. Horizontal asymptote pi over 2. Now let me ask you all a quick question. This graph, is it always increasing, or is it increasing sometimes and decreasing other times? It's always increasing. Its derivative is always positive. But if you pick a negative x value there, you're going to get a negative result there. So for this derivative to be correct based on this choice, which we'll talk more about on Thursday, you need an absolute value there. And it's just the way it is. So depending on what your instructor says, it could be that your derivative of arcsecant is 1 over the absolute value of x times the square root of x squared minus 1. Or it could not have the absolute value if you pick the other graph, which I'm not going to talk about because we're out of time. But we'll talk about it on Thursday. So there's your inverse trig derivatives. Thursday, we'll talk a little bit more about them, and then we'll talk about some related rates. Have office hours as usual. Make sure you sign your name on the sign-in sheet, wherever it's gotten to, the makeshift sign-in sheet.